Welcome dear viewers. We are continuing with transition and inner transition elements. In this module, we are focusing the chemistry of actinide elements. As we are aware, inner transition elements are in two series. They comprised of elements from atomic number 58 to 71 and other group comprised from atomic number 90 to 103. Inner transition elements or F block elements are generally placed as two rows below other elements in the periodic table. They include elements of atomic number 58 to 71 designated as lanthanides and atomic number 90 to 103 denoted as actinides. Here, in the case of inner transition elements, the last electron or outermost electron added to F subshell of the anti-penultimate shell. The actinide series. These are a group of 14 elements beginning from thorium with atomic number 90 and ensign lawrencium with atomic number 103. These are named so because these elements succeed the element actinium. So, elements coming after actinium are named as actinides. These elements are also known as second inner transition series of elements. These are the actinide elements. Actinium, after that the first actinide, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium and lawrencium. In the case of actinide elements, the 5F subshell of the antipenultimate shell, that is n is equal to 7, is successively filled. The ultimate and penultimate shell of these elements has number of electrons remain approximately or almost the same. That is why actinide elements show very close resemblance in their reactions, physical as well as chemical properties. The electronic structure of actinide elements. The general electronic configuration can be represented as radon core 5F0 to 14, 6D01 or 2, that is 0 to 2 and 7S2. Simply note that here 7 represents the ultimate shell, 6 represents the penultimate shell and 5 represents the anti-penultimate shell. On carefully analyzing the electronic arrangement of actinides, it is clear that the actinides having gradually increased 5F electronic arrangement. That means the 5F subshell is gradually filled from 0 to 14. The first element thorium has no F electrons and it has an electronic arrangement 6D2 7S2 along with the radon core. Some elements protactinium, uranium, neptunium and curium, on analyzing the electronic configuration, we can see the presence of 6D1 arrangement. Also lawrencium got a 6D1 arrangement. From this electronic configuration of actinides, we can arrive at the conclusion that as in the case of lanthanides, we can't observe any regularity in electronic arrangement of actinides. The electronic configuration of actinium, that is the precursor of actinides, is radon core with the 5F0, 6D1 and 7S2 arrangement. Some of the elements have exceptions associated with the filling of F orbital as well as the d orbital. The outer electronic configuration of actinide can generally represented as I mentioned radon core 5F1 to 14, 6D0 to 2 and 7S2. The electronic configuration of actinides does not follow simple pattern as we observed in the case of lanthanide elements. For the first 4 lanthanides, that is thorium, protactinium, uranium and neptunium, due to almost equal energies of the 5d and 6d subshells, electron may present either in 5f or in 5d or both in 5f and 6d. Now, trans-uranium elements. The elements coming after uranium are simply termed as the trans-uranium elements. That is, elements with atomic number higher than uranium are called trans-uranium elements, and the trans-uranium elements are artificial elements. Whenever we are analyzing the actinide series, we can observe that there are 11 trans-uranium series in actinide series. Such trans-uranium elements are depicted here: neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium and lawrencium. Now let us have a glimpse on the general features of actinides. As we studied in the case of lanthanides, actinides also have some general features. Now we can outlook into the general features of actinides. First of all, occurrence of actinides. Only the first four elements, namely actinium, thorium, protactinium and uranium, occur in nature in several uranium minerals, out of which thorium and uranium occur to any useful extent. That means other elements exist only in trace amounts. All the remaining actinides, that is trans-uranium elements, that means element coming after uranium, are highly unstable and are made artificially. That means trans-uranium elements present in the actinide series are man-made elements. Regarding the oxidation state, actinide elements show different oxidation state. All of them are not equally stable. Some oxidation states are highly stable, some other oxidation states are highly unstable, and the oxidation states are enlisted here. Regarding thorium, the oxidation states shown by thorium is +2, +3 and +4. For the first few elements, there is a versatility in the oxidation state. But for the succeeding elements, the common oxidation state is fixed as +3. Regarding oxidation state, we can arrive at some conclusions. Some of them are stable, but some of these oxidation states are unstable. The +2 state is exclusive for thorium and americium. The +3 state is exhibited by all elements and it becomes more and more stable as the atomic number increases. That is towards lawrencium, towards the last elements, with increase in atomic number, the +3 oxidation state dominates. The +4 oxidation state is shown by elements from thorium to berkelium. The +5 oxidation state is shown by elements from thorium to americium, and the +6 oxidation state is shown by elements from uranium to americium. The +7 state is exhibited by only two elements, namely neptunium and plutonium. Atomic radii of actinides. As we know, atomic radii is the distance from the center of the atom to the outermost electron. Whenever we are analyzing the atomic radii values of actinides, we can arrive at some conclusions. Atomic radii first decreases from thorium to neptunium and then increase gradually up to berkelium. This is depicted in the picture. For thorium, the atomic radius is 180 picometer. For protactinium, it is reduced to 164, and this diminishing observed up to neptunium. After neptunium, the next element plutonium has atomic radii 160. There is an increase is observed. And for californium and higher elements, one or two elements, the exact value of atomic radii is not known. Regarding ionic radii represents the shortest distance from the center of the metal, from the center of the ion to the outermost electron. The cationic radii, that is radii of the trivalent cation as well as radii of the tetravalent cation, is shown here. For the trivalent cation, from thorium to californium, we can see a marked decrease. This type of decrease is also observed in the case of tetravalent cation. And it is clear that the size of the tetravalent cation is also less than corresponding trivalent cation. That is, there is a gradual decrease in ionic radii for both the trivalent and tetravalent cation as we proceed from thorium to californium. The values of ionic radii of both the type of ions goes on decreasing with increasing atomic number. This steady fall in ionic radii along the actinide series is termed as actinide contraction. Such a type of contraction we observed in the case of lanthanides, and we named there as lanthanide contraction. The abnormal decrease in size along the lanthanide series is said to be the lanthanide contraction. Imperfect shielding offered by the 4f electron is responsible for the lanthanide contraction. In a similar way, by analogy with the lanthanide contraction, we can also observe contraction among actinide series, and that is theoretically termed as the actinide contraction. It should be noted that the actinide contraction is not at all dominating or systematic as in the case of the lanthanide contraction. Actinide contraction is pictorially depicted here. The cause of actinide contraction is same as has been discussed in the case of lanthanides. That means imperfect shielding offered by the F electron is also responsible for actinide contraction. The contraction is pictorially represented like this, and there is no much size difference between the first cation and the last cation. Similarities among lanthanides. There is very small change in the radii of actinides. Either atomic radii or ionic radii, there is a very small change. And as a result of this very small change between actinide ions, we can conclude that there is no much size difference between two adjacent members of the actinide series. As a result, what the effect is, the chemical properties of actinides are quite similar. If the chemical properties are similar, we can't separate actinide ions by common methods as we observed in the case of lanthanides. But actinide contraction is not dominating as lanthanide contraction. Hence, the separation of actinide is not at all a difficult task as in the case of lanthanides. Radioactivity in actinides. Most of the actinide elements are man-made elements or synthetic elements, and as a result, they are associated with the phenomenon of radioactivity. Emanations, radiation emanation from metal nuclei or atomic nuclei is simply termed as radioactivity. Radioactive isotopes have fixed value for their half-life period, and the chart represent half-life periods of longest lived isotopes. See, for an element, there may be more than one isotope, and these isotopes have different half-life, and the chart represent half-lives of long-lived isotopes of actinides. And from the chart it is clear that thorium, the longest lived isotope is thorium 232. Completely it is designated as 90 thorium 232 with a half-life of 1.4 into 10 raised to 10 years. That is the highest half-life period ever observed for a stable actinide isotope. At the same time, just look into the last element, lawrencium isotope 103 lawrencium 262. That isotope has a very short half-life period, and that is comprised of only 3 minutes. So, the shortest lived isotope is lawrencium 262, and longest living isotope of actinide family is 232 thorium. Magnetic properties of actinides. As we all aware, magnetic properties is caused by the presence of unpaired electrons in the element or in the ion. The actinide elements like lanthanides show paramagnetism in the elemental as well as in the ionic state. Tetravalent thorium, TH4, and hexavalent uranium, uranium plus 6 ions are diamagnetic. This is exclusively due to the absence of unpaired electrons in them. Spin orbit coupling interaction, that is, for the magnetic property, contribution from two areas is very important. The spin contribution as well as the orbital contribution. And in the case of actinides, the spin contribution and orbital contribution together make net magnetic moment. That is, spin orbit coupling interaction is strong in the case of actinides. Regarding the electronic spectra of actinides, as we know, electronic spectra is due to electronic transition. Electronic transition means transition of an electron from a particular low energy level to a high energy level. For the electronic transition to occur, there must be some energy is required, and that energy is absorbed from the visible light. So, a visible light fall on a particular lanthanide ion or lanthanide atom. Electron situated in a particular energy level absorbs that energy and will get excited. As a result of the excitation, energy is absorbed. But as we know, the excited state is highly unstable and the lifespan is about 10 raised to minus 8 seconds. So, after that lifespan, the electrons from the excited state start de-excitation. That means it starts removal of its energy or liberation of energy. As a result of the liberation of energy, some complementary colors are observed. On carefully analyzing the possible electronic transitions governing to electronic spectra of actinides, we can arrive at the fact that there are three possible electronic transitions that leading to electronic spectrum, and such transitions are the F transition, that is transition between different F orbitals. Next, 5f to 6d transition, that is a transition from a 5f subshell to a 6d subshell. Then metal to ligand charge transfer transition. Charge transfer transition simply means electronic transition. Metal to ligand charge transfer means electrons are transferred from the central metal of a coordination complex of actinide to high energy pi star antibonding orbitals of the ligand present in the actinide complex. So, these three transitions govern the electronic spectra of actinides. We can enter into details of each and every electronic transition possible in actinides. First of all, the FF transition. The FF transition is Laporte forbidden. That is, the transition is restricted by the Laporte selection rule or parity selection rule. The Laporte selection rule says that for an electronic transition to occur, delta L should be equal to plus or minus 1. But for F orbitals, since both are F orbitals, the orbitals participating in FF transition are both F orbitals. That's why delta L is equal to 0. L means azimuthal quantum number. For the first F orbital and the second F orbital, azimuthal quantum number remains the same. The value is 3. Therefore, delta L is equal to 3 minus 3, that is equal to 0. This, as per theory, Laporte rule will not permit the FF transition. However, there are some cases where Laporte selection rule got relaxation, and this relaxation is due to crystal field effects, distortion effects that occur during the complex formation. That is, crystal field effects affect the symmetry of the central metal actinide ion. So, if there is some relaxation occur for Laporte rule, that transition, that FF transition may happen. Since the FF transition is Laporte forbidden, the intensity corresponding to that transition will be minimum. The next transition, that is 5f to 6d transition. The participating orbitals are 5f and 6d. For F subshell, azimuthal quantum number is equal to 3, and for D subshell, azimuthal quantum number is equal to 2. Therefore, delta L is equal to -1. As a result, it is clear that the 5f 6d transition is perfectly Laporte allowed. Moreover, the 5f 6d electronic transition in actinides is also allowed by another selection rule, that is spin selection rule. The spin selection rule says that during electronic transition there should not be any change in total spin multiplicity. So, the 5f 6d transition is permitted by both the Laporte and the spin selection rule. Hence, these transition occur with very ease, and as a result the transition leads to highly intense signals or bands, and these transition occur with very low energy, and that signals confined in the UV region. Since the signals are confined in the UV region, this electronic transition will not affect color of the actinide ions. Metal to ligand charge transfer transition. This is the last type of transition responsible for electronic transition in actinide compounds. These transitions are also fully allowed by the previous set of selection rules, namely Laporte and spin selection rule. It usually found in UV region, and sometimes the metal to ligand charge transfer transition appears in the visible region. They produce intense color which are characteristics of actinide complexes. Color of actinide ions. Definitely the electronic transition or electron spectra that appears in the visible region is responsible for the color shown by actinide ions. Most of the actinide cations and their salts are colored due to FF transition. Even though it is forbidden by Laporte rule, FF transition occurs due to some relaxation, and that relaxation produces color, and hence we can conclude that most of the cations are colored due to the so-called FF transition. However, the cations with the configuration F0, F7 or F14. F0 means there is no electron for a transfer. F7 is a stable half-filled subshell arrangement. F14 is completely filled highly stable arrangement. So, for these three configurations, practically there will be no FF transition, and hence the cations or salts with this configuration appears to be colorless. Moreover, the color depends on oxidation state also. Same cation in different charge or same element in different oxidation state produce different colors. The reason is simple. As the number of unpaired electron changes, the possibility for transition also changes, and hence color may vary. For instance, plutonium 3, plutonium 4, 5, 6 and 7 shows different colors as given here. That is, same element under different oxidation state produce different colors. Some may be colorless, some may be more colored, some may be differently colored, etc. Reduction potentials of actinides. Reduction potential. What do you mean by the term reduction potential? The tendency of a ion to get reduced, the tendency of an atom to get reduced. simply the tendency to get reduced is termed as reduction potential. The chart depicts the reduction potential values of actinides, and for thorium and protactinium the data is not known with certainty, and hence it is excluded from the chart, and all the reduction potential values are negative. The opposite quantity of reduction potential is oxidation potential. Oxidation potential represents the tendency to get oxidized. Since the negative values are for reduction potential, oxidation potential values are definitely positive. That means all the actinides have a greater tendency to get oxidized. This represents the reduction potential of M3 plus 2 metal. That is the tendency of reduction of metal 3 plus ion by capturing 3 electrons to get metal M. The reduction potential values are negative, so oxidation potential values are positive. That means the metal has a tendency, greater tendency to convert it to metal 3 plus. We can arrive at some important conclusions from this reduction potential data, and the negative reduction potential for this M3 plus M indicates that the following process is possible. Since reduction potentials are negative, oxidation potentials are highly positive. So metal has a tendency to get converted to trivalent cation. So whenever we are taking some actinide metals and react with some dilute acids, what actually happened is metal is converted to metal salt and hydrogen gas will be liberated. And we can conclude that the metal, actinide metal, all react with dilute acid and they will set hydrogen gas free, because all these metal have high oxidation potential. Ionization enthalpy or ionization energy of actinides. Ionization energy is a quantity that represents the amount of energy required to ionize, required to remove most loosely bound electron from an isolated gaseous atom. The values of first ionization enthalpy of actinides in unit of kilojoule per mole is given here. For actinium, the ionization potential is 499 kilojoule per mole, that is comparatively low value. From thorium onwards, we can see an increase in the ionization potential values, but that increase continues up to the second last actinide, that is nobelium. However, for lawrencium, the ionization enthalpy value is lowest, first ionization enthalpy value is lowest, and that is 444 kilojoule per mole. And this lowest value is due to a loosely bound outermost electron in its electronic arrangement. Complex formation tendency. As we studied in the case of actinides, lanthanides also have complex formation tendency. Because of wide range of oxidation state available, their coordination chemistry is highly variable and highly varied or more varied. Most of the actinide halide form compounds with or complexes with alkali metal halide. That is, there is a possibility for the combination of actinide halide with alkali metal halide to get a coordination complex. Chelates are formed by actinides with multidentate ligands like ethylene diamine tetraacetic acid, that is EDTA, acetyl acetone, etc. So there is wide variety of coordination complexes in actinides. The actinides with the small size and high range have greatest tendency to form complexes. The degree of complex formation follows the order M tetravalent, M4 plus greater than, MO2 2 plus greater than, M3 plus, and the complexing power of different anions, different univalent anions follows the order F minus greater than, NO2 minus greater than, Cl minus. So best combination M4 plus with F minus, excellent and stable complexes are produced. binary compounds of actinides. Actinide elements are highly electropositive and reactive. They have much higher tendency to form complexes. However, they form different kinds of binary compounds such as oxides, halides, hydrides, nitrides, etc. First of all, oxides. The metal, actinide metal, on reaction with the air or oxygen give various oxides under different experimental conditions. So, with the change in temperature, the molecular formula of oxides may different. For instance, uranium is one of the reactive element and it will give oxides with the formula UO, UO2, U3O8, UO3, etc. Other oxides are also reported. Neptunium oxide NPO, NPO2, plutonium oxide PuO and PuO2 and americium oxide AmO2. Regarding hydrides, uranium and plutonium form hydrides by the direct union of the elements. Uranium reacts with the hydrogen even at room temperature to produce their hydride. 2U plus 3H2 gives 2UH3. Halides, they are formed by the direct combination of halogen with the actinides, the most common being uranium and neptunium. Trihalides MX3 are common, tetrahalides, pentahalides and higher halides are also reported. Now there is a comparison between actinides and lanthanides. Both of them exhibit a +3 oxidation state as the predominant state. Like lanthanides, actinides also exhibit actinide contraction. Both the contractions are due to imperfect shielding offered by the 4f electrons. The elements of both the series are quite reactive and electropositive. The electronic absorption bands of these elements, both the series give sharp lines. Most of the lanthanides and actinide cations are paramagnetic. That's all about the present discussion on actinide chemistry. That's all. Thank you.